So anything that any chemical that when placed in water produces what is called we call it a proton or an H plus ion. Okay. Now, how does that happen? Well, let me share with you the whiteboard. Okay. We know that hydrogen has one electron. Okay, it's the very first atom. We also know that the electron configuration is 1s1. Okay. Now, if you recall from the periodic table, we put hydrogen in group 1 because it is not a metal, though. Remember, it's not a metal, but when it shares with everybody else in group 1, it has one valence electron, like everyone else in group 1A. Okay, hence we put it there. Now, recall that the s orbital has the capability of handling 2 electrons. Okay, right now the s orbital only has 1 electron. So what's unique about the hydrogen atom is that it can pick up another electron and literally fill that orbital up. And guess what? Because it has an extra electron, like we've been doing, it's got 1 proton, 1 electron to begin with, but now it has an extra electron. Now it has a net negative charge because of that extra electron. And that has its own little name where you have a hydrogen with a negative charge. And just like the other ones, remember the chlorides, the oxides, all those nonmetals, when we change the name, we change this one to hydride, okay? That's one unique property about hydrogen atom, that it can pick up 1 more electron because it has that s orbital empty. It has room for 1 more. I should say empty, it has room for 1 more, okay? Now, at the other end of the spectrum, because it has 1 valence electron, it can very readily lose that 1 electron. And so this time you end up with 1 proton, no electrons, with a net charge of a plus, right? The s orbit now is empty, got a 0 up there. It's empty, and there's no electrons in there. And this has its own little special name that we call a proton. Okay, and so the hydrogen that has lost that electron is called a proton. Okay, and so you're going to hear me say that name quite a bit. Instead of calling it hydrogen plus, we call it a proton. And this is the guy, this is the chemical, the species that causes something, a chemical, to be an acid. Now, remember also that when I talked about ionic compounds, okay, ionic compounds are ionic in that they have a full negative and full positive charge. So when they go into water, they totally dissociate. Some of them dissociate 100%, some much less. Nevertheless, they break up, okay? And at that time, I said, that's the difference between an ionic compound and a covalent compound. And that is protons, covalent compounds do not break up, okay? In step 1 accepted, and that is covalent acids. Covalent acids are the only covalent compounds that break up into a completely separate charge, just like the ionic compounds. And that's what causes the acidity of anything, is anything that produces a proton when we dissolve it in water. Okay, so, and that's what you see here, H plus, and that is why we have an H plus, because there's no more than the electron of the hydrogen that has been lost. As a positive charge, it is a cation. And the unique thing about hydrogen, like I stated, it can be a cation. At the same time, it can also be an anion depending on the conditions. So we call this guy a proton. Some of the things about acids, well, very sour taste. Obviously, you know, lemons, sour taste. Even if you're not feeling right and you happen to regurgitate some of your stomach acid, very sour and burns, actually. Burns in your esophagus, okay? Very corrosive. They tend to want to react with metals and break them down, cause a reaction, very corrosive, okay? Now, one way to determine whether a solution is an acid or not, we have pH paper, but there's one pH paper, is we call it blue or red litmus paper, just litmus paper. It doesn't tell you the extent of acidity because we're going to learn that acidity has a pH, has a value range, okay? So a litmus paper simply tells you whether it's a base or an acid. That's it. And so if you were to take a solution and put some blue litmus paper in it, the paper would turn red. And that all that does is indicate to you that you have an acid. Doesn't tell you how strong it is. Okay. Now, remember this polyatomic ion? OH negative? Yeah. Okay. The hydroxide. So the hydroxide definition of a base is any chemical that when put into an aqueous solution. Now, when we talk about acids and bases, we are talking about an aqueous solution, a water-based solution. We're not talking about acidity in a different type of solvent system, only water, okay? So when we put something in a chemical in water and it breaks up, dissociates is the term we use, and one of them, if they produce a hydroxide ion, that is classified as a base, okay? There's a lot of those out there. Liquid plumber, good example. If you ever used it, that is a very strong base. Be careful with it. In fact, if you ever get liquid plumber in your finger and in your skin, I feel slimy. And you'll say, people will tell you, well, that's the chemical that makes it slimy. And no, it's not the chemical. It is the tissue that sodium hydroxide is breaking down, okay? And breaking it down, that's why it feels so slimy. It's your own tissue. So if you get any on you, wash it off immediately. I wouldn't recommend tasting it, but it does have a bitter, chalky taste to it, okay? And again, it feels soapy and slippery, again, because it feels that way because your tissue is being broken down. Now, the other type of litmus paper that we have is the red litmus paper. And the red litmus paper is always going to tell you if it changes to blue, then that solution is a base. If it stays red, it's still whatever it is not a base. And the same is true for the blue litmus paper. If it stays blue, then more likely it's a base, but it's not an acid if it changes to red. So that's all litmus paper tells you, base or acid. That's it. All right, so definition, the first one, Arrhenius acids and bases. Now, this is what we mean by the acid put into solution breaks up into the ions, okay? It dissociates. Hydrochloric acid, okay, is the same acid that's in your stomach. And so when normally it's a gas, but when you place it in water, it goes into solution. And when it does, it breaks up. And when it breaks up, it forms the two ions. It forms the proton right here, which is the acid part. And then it forms the corresponding anion, which is the chloride, okay? And the H plus, the proton, is what makes it acidic. So any acid that produces a proton in an aqueous solution is by definition, by Arrhenius definition, an acid. Okay, we're going to have a different definition here. We got two definitions that are going to encompass a lot more chemicals that can be defined as an acid or base. But the original definition was anything that produces a proton. Okay, now anything that produces the hydroxide ion, the polyatomic ion, in an aqueous solution, that's key, aqueous solution, is by definition an Arrhenius base. And so you have sodium hydroxide in the solid form. You place it in the water, okay, and it dissociates and it produces the hydroxide, polyatomic ion. Okay. Now, oh man, let me ask you a question here. Let me see something real quick. Oh, now maybe you can recognize something here, but let's see. I'm going to put this. Now, you notice we just said it produces a proton. So a proton is an H plus. And if we combine it with the hydroxide, which is a negative plus, would anybody want to take a guess as to what the product would be? Let me give you a hint. We got tons of it on Earth. You have tons of it. No, maybe not tons, but you have a lot of it on your body, in your body. You may be drinking some of it right now, like I am. Oxygen, not quite. See, proton, break it down. You got a proton with an H plus. You got an OH with a negative. They're going to attract each other to form a compound. Okay. What compound do you think they're going to make? That has, when you put them together, there you go, water. All right. Exactly. And so you got the H plus combining with the OH negative to generate H2O. Okay. That, ladies and gentlemen, is your first type of reaction that we're going to eventually talk about. This is called the neutralization reaction. Okay. That is when a proton and hydroxide combine and they neutralize each other. Okay. For example, you got acid in your stomach. You got a lot of protons in there. You have too much acid reflux or something, and you want to reduce the acid concentration. What do you drink? You drink a base, hydroxide, either in the form of magnesia or calcium hydroxide, or with Tums, for example. Okay. And what happens? That acid gets neutralized, you form water. So, all right, good. Let's see, let's clear this out. Now, neutralization is exactly what I was just talking about here. Okay, I wanted to bring it up a little bit. Hopefully you can see how we figure that out. But here it breaks it down. In general, when you have an acid and a base, when they combine, they form what we call a salt. Now, a salt, in this case, the example is sodium chloride. But remember, term salt, it does not mean the table salt you put on your French fries all the time in chemistry, right? It means this term. That is an ionic compound. So it's a metal, non-metal combination. So you may not always have sodium hydroxide. This could be potassium hydroxide. This could be lithium hydroxide. It could be anything, but you form a salt, okay? And so we got the proton coming from the hydrochloric acid, HCl. You got the hydroxide coming from the sodium hydroxide. And they combine, like I just showed you, to form water. And then the corresponding salts remain. So you got sodium chloride. And we're going to learn that sodium chloride is soluble in water, so they're going to stay as ions in solution. Okay. The main ones that are doing anything R is the hydroxide and the proton. They get together, neutralize each other, and create water, form water. Okay. And then we have the salt, which is the sodium and the chloride combined, and just have these sodium chloride in solution. Okay. So remember, a salt is not necessarily always sodium chloride. It's an ionic compound, a combination of a metal and a non-metal. Okay, now we're using this definition, Arrhenius, and that encompassed quite a bit of chemicals. However, it did not encompass others that acted as a base and had nothing to do with protons or nothing to do with hydroxide. Notice the Arrhenius definition, we produce a OH minus, a hydroxide ion. Not all chemicals do that, but still can neutralize acids, okay? And so there had to be a different type of definition that encompassed more examples of compounds that were a base. And hence, this was created by Brownstein and Lowry. And so we have a definition called the Brownstein-Lowry acid and base. Now, they both share the same similar definition for an acid, okay? In that, in Arrhenius definition for an acid is anything that produces a proton. Well, Arrhenius, what they're saying, anything that loses a proton. It's the same thing. You're making a proton. All right. So that's open to argument. That's fine. But you're making a proton. Bottom line. Either you lose it or you produce it. Same thing. Okay. Where they differ is how they define a base. Arrhenius said anything that produces a hydroxide ion. What the base says, what Brownstein-Lowry says, any chemical that accepts that proton is defined as a base. And that opened up a lot of more chemicals to be based. For example, look at the example we have here. We have hydrochloric acid, HCl, and then we have NH3. This is a while back. We were doing the Lewis dot structure on this. This is ammonia, okay? And when we did the Lewis dot structure, you might recall, let me see if I can draw it here. We ended up with 2 lone pair on the central atom, which is nitrogen, 2 lone pair of electrons. Okay? It comes into play here in a minute. And what happens is the proton produced by hydrochloric acid, which is right there. Remember, when it becomes H plus, remember that 1s orbital is empty. Remember the first example I had? It's empty. And guess what happens? The lone pair on the nitrogen of ammonia insert those lone pair into the empty orbital of the proton and form a complex, a bond. And so you end up with, and we drew the Lewis dot structures for this. Well, back, this is the ammonia. And we drew the Lewis dot structure, and we had nitrogen bonded to hydrogen. Oh. We have hydrogen, 4 hydrogens around the nitrogen, okay? And then we drew the Lewis dot structure with the plus charge. That lone pair, that it could be this one, we can say that one for right now. It could have been any of these 4, but let's pick this up. That lone pair that was on the nitrogen, that hydrogen that lost its electron has that empty orbital, so it can come in there You know, so we got the hydrogen sitting here with an empty orbital, if you will, okay, where the electrons used to be. And then we got the lone pair of the nitrogens here, creating this bond complex or the ammonium ion. Okay. And so now we see that there's chemicals out there that have lone pair that can act as a base. And it really, this definition encompassed a lot more chemicals that were bases. Even the original one where we had the proton and the hydroxide. Think about it. The hydroxide had lone pairs all the way around it. Cancer gave it the negative charge. And so we can easily form a bond right there. Okay, and that's what happens. Yeah, that lone pair on one of the lone pair on the oxygen created a bond with the proton, which is happening down here with the ammonium salt. Okay. All right. So to rehash, Brown-Sedlowry acid-base definition, an acid similar to the Arrhenius definition loses a proton or creates a proton. Okay. The difference is the base. In the Brown-Sedlowry definition, hydroxide is not a factor. Okay, hydroxides are not a factor. It is any chemical that accepts that proton. And here we have the example of ammonia with the lone pair. So criteria number one is to accept that proton, you have to have lone pair on the central atom, someplace, somewhere. Otherwise, it will not work. Okay. All right, so hydrochloric Hcl loses proton, and the ammonia, this is ammonia, gains a base. So this should tell you something here, real life situation. Ammonia is pretty strong odor, okay? And what happens, for example, cats make dogs making a mistake around your house and not cleaned up, you get the smell of ammonia. Well, what's happening there, bacteria breaks down another chemical in the urine, and one of the products is ammonia, and that's what you're smelling. Same is true with baby diapers. One way to get rid of it is to react that ammonia with an acid that you have at home, and the perfectly good acid is vinegar. Okay, you form a salt. By forming a salt, the ammonia now is not as volatile. The salt is not as volatile, and that reduces the odor of ammonia. FYI. All right, now we have what are called strong acids and strong bases. This is the beginning of these chemicals that we're going to start learning about why we classify them as strong and why they're called, we got strong and weak, okay? We're going to talk about strong acids and bases first. All that means is when they are placed in the water solution, they dissociate completely, almost to 100%. Okay. And so here's a couple of three of them here that you may want to get to know their name. First one was called HCl, Hydrochloric Acid. Okay. The second one is HNO3, is called a nitric acid. And then the third one with the formula H2SO4 is called sulfuric acid. Now, a question to remember here to help you out to define, when the way they're written out, you say, well, how do I know that that is an acid? Okay, because what we've been doing so far is when we draw say an ionic compound, we draw the metal first, followed by whatever is bonded to the metal, okay, or attracted to the metal. Or in the covalent compounds, we said, all right, we generally, you'll find the central atom, and then whatever is bonded to the central atom follows that. The only exception at the time was water, H2O, that by convention, it's written in that manner, hydrogen first. All right. when it comes to acids, you'll find that the hydrogens are in fact written first. You can see we got hydrogen here, followed by chloride. We got the hydrogen followed by the NO3, which by the way is the nitrate ion. Okay. A lot of these anions originally are acids. When you react with a base, you form the corresponding anion. Look at this one, it has two hydrogens in front of it. If we were to remove those two hydrogens, guess what? Look, SO4 -2. Isn't that the sulfate ion, right? Okay, sulfate ion. And so there's three examples here of strong acids in that they completely dissociate 100%. Okay. And some examples of strong bases. The majority of bases that you're going to be dealing with are ionic compounds. They're going to have the polyatomic ion like hydroxide. So here, potassium hydroxide, sodium hydroxide. These are two examples of very strong bases. So when they go in water, they completely dissociate into the ion. Approximately 100%, but pretty close. And that is what makes them classified as strong acids or bases. Okay, now how do we draw that with respect to diagrams? Well, here's an example. We have hydrochloric acid. By definition, we know it is a strong acid. And so we can demonstrate that by writing in, I don't know, 3 or 4 pairs of ions. Notice they're totally separated. You've got 3 chlorides and 3 protons. When you write these or draw these, make sure you put the charge on them and make sure they're separated. Because combined together, remaining as HCl infers something else, that they're not soluble, okay? The fact that they completely dissociated, they're completely 100% soluble in water, is shown by this diagram on the left, where the ions have got at least 3 sets of ions, a positive set and the negative set. Same is true on the right side. Okay, sodium hydroxide, otherwise known as lye solution, very strong base. In fact, a lot of makeups I'm learning that have hydroxide in them, and that's to kind of, I guess, peel the skin a little bit, get rid of some of that skin. I don't know. Not as strong as some of the hydroxides out there, but it's enough strength to clear up the skin, I guess, to get rid of old tissue. Anyway, on the right side demonstrates the proper way to write sodium hydroxide in a solution in a beaker. This is assuming you got a water beaker here, and this represents water. It's a water solution. Okay, and maybe move it down a little bit. Okay, wholly 100% dissociated. Infers strong base on the right because hydroxide is generated, okay, and a strong acid on the left because you generate a proton, okay, and they're completely dissociated, so that infers that both of them are strong. Okay, so those are the 3 I just talked about: HCl, hydrochloric acid, HNO3, nitric acid, and H2SO4, otherwise known as sulfuric acid. Notice the protons, the hydrogens are written first here. The bases I just gave you, sodium hydroxide and potassium hydroxide. Okay. Again, what does strong mean? That means that the ions are 100% dissociated. I mean, the chemical dissociates completely, and respective ions are generated. Now, on the other end of the spectrum, we have what are called weak acids and weak bases. The only difference between the two, they're both acids, they're both and bases. The difference is the amount the amount of ions that are produced. The strong ones produce 100%. The weak ones produce much less, 1 to 5%. Okay, it still produces the ions, but the majority of the ions are still held together as a unit. Some examples are those. First one is HF. It's hydrofluoric acid. If you ever stain glass, for a hobby of some sort, that's the chemical that you're using. H2CO3, you drink a lot of soda pop like me, it's carbonic acid. Every time you carbonate water, you have these machines that you have a cartridge of carbon dioxide and bubble CO2 through the water to give you carbonated water. You actually are creating carbonic acid in there. The third one, again, written with a hydrogen in front. Then you got 2 carbons, 3 hydrogens, and 2 oxygens. That is a general formula. Again, a general formula for something that, if you like Italian dressing, that's what you're eating. That's called acetic acid, aka vinegar. Okay, acetic acid. And then H3PO4. That's also, you find a lot of that in soda pop. Phosphoric acid. Notice something. The second example, H2CO3. If you take those 2 hydrogens off, the protons off, you end up with CO3 and -2. Guess what? Look at your polyatomic ion, carbonate ion. If you look at the second one, take that proton off in front of the acetic acid, you end up with C2H3O2 negative, because that's an ion, that's the acetate, also on your polyatomic ion. And then finally, the last one, the PO4 -3, also on the table is the phosphate ion. Okay, so these ions came originally from an acid, HF. If you react HF with the base, you end up with F-, fluoride. Okay, all right. So here's the difference between the two. In the other examples that we did, we used a one-way arrow to demonstrate it went over to 100%. 1 second. Okay. To demonstrate that it went to 100%. What we're using here is a double directional arrow right there, which is telling you that it's going in both directions, that some of the impact here, in this case, acetic acid, goes over, dissociates, produces the proton. Let me change that to a different color. Produces the proton and the corresponding anion, which in this case is the acetate anion, okay? But the majority of the material is still intact as acetic acid. And hence we have the double arrow. So roughly from 1 to 5% of this material has ionized. This is what makes it a weak acid, because it doesn't have that much ions in solution. Now, how do we show that? Oh, before I do that, here's another example of an ionic compound, okay, that we would think, okay, it's ionic, it should go into water 100%. And I said earlier that in the beginning, I said ionic compounds will dissociate in water, but we're going to learn, I also stated that some of these ionic compounds dissociate 100%, like sodium chloride, and then some much less. And here's one example of an ionic compound that you would think would dissociate 100%, but it doesn't. It has to do with the solubility of it in water, so much less. So magnesium hydroxide is a good example of a ionic compound that does not dissociate 100%. And so, yes, the majority of the material is still intact and it's still solid. You might you might have used some of this before. Magnesium hydroxide, which is milk and magnesia. If you ever get a glass of milk and magnesia and pour some into a glass, let it sit there, it'll separate, okay? Because the bulk of it is still intact. You have to shake it up to get it into an emulsion so you can ingest it. You do have some ions, but not very many. Okay, we have the double-sided arrow here. And then we have some of the corresponding ions, which is the magnesium and 2 hydroxide ions. Why 2? Because it starts off with Mg parentheses OH2. There are 2 hydroxide ions for every magnesium ion. Now, some people have a challenge with this part right here, but think of it this way. And the compound magnesium, magnesium hydroxide intact. Think of it as a bicycle with 2 tires, right? Two-wheel tires. All right. Well, intact, I got magnesium that is represented by the bicycle frame, and then the hydroxide is represented by the 2 wheels, two-wheel bicycle. Well, what happens is when we take those wheels off, we end up with the frame, okay, right? And guess what? 2 wheels, 2 tires. Well, this is analogous to that, to magnesium hydroxide. And that's the thing that we got to remember here, because you could have 1-to-3 ratio where you have like a tricycle, if you will, where you got the main frame and 3 wheels, or you can have a 1-to-1 ratio where you have the bicycle a unicycle where you got the frame, unicycle, and 1 tire, right? There's depending on what you started off with and what's in the parentheses. So yes, that's where that 2 comes from. All right, so how do we represent these weak acids and weak bases in diagrams? And we do it as follows. On the left is an example of a weak acid. We have to identify it first. That is a weak acid. HF, by definition, we gave you the examples of weak acids, is a weak acid. And so we need to draw that in a diagram. You can draw as many as you want. I don't know, on the average, it'll take 4 or 5 pairs of molecules. So, but because it's weak, we would find maybe 1 set of ions in solution. Okay, 1 set of ions. And don't forget the charges on them. Just leaving the hydrogen up there would be incorrect. And the majority of the rest of them, I'm going to change color here so we can distinguish them, are intact. They've not been separated, okay? So in this example, we have what, 1, 2, 3, 4, 5 set that are intact and only 1 set that has separated and dissociated. All right, excuse me. Now, with respect to ionic compounds, and this is what happens when you find covalent compounds that are weak, okay? They're still floating around in solution, but they're not dissociated. When you are working with ionic compounds that are not soluble or not very soluble, we draw them as follows. Notice the equation that you see up here. Let me highlight a couple of things. Notice the state of magnesium hydroxide to begin with, S, solid. Notice the state after it's dissociated, AQ, aqueous, meaning they're in solution, okay? Now, what we do is, because we know that it's a weak base, the majority of it is drawn like the bottom here, sitting in the bottom of the beaker. It's a solid. And we're going to learn about solubility here in a second. It's a solid. It's actually a white powder sitting there at the bottom of a container. That's what I said. If you take some milk and magnesia, pour it into a glass and let it sit there, the white powder will settle into the bottom part of your glass with the clear liquid on top. Okay. Now, in solution, there's at least 1 pair, and that shows it that, yes, it's ionic, but there's not a lot of them. There's only one pair here, okay, of the magnesium hydroxide in ionic form and in solution. So the one on the right shows it, one, demonstrates it's a weak base. And furthermore, the fact that it is, you drew it with some gunk in the bottom of the container, if you will, some solid material, that shows you that it's insoluble, okay? The same is true with the HFs that are on the left side that are intact. It's weak and insoluble. Yes. Now, when I say insoluble, it doesn't mean 100% that nothing goes in solution. Insoluble just means that the majority of the material does not go in solution. It stays intact. You may get 1 to 5% in solution, a few molecules in ionic form. Okay. All right. Some examples of the weak acids and weak bases I mentioned to you: hydrofluoric acid, carbonic acid, phosphoric acid, and acetic acid. And notice how they're written with the H up front, okay, first. And check this out, CO3 minus 2, carbonate. PO4 minus 3, phosphate. C2H3O2 negative, acetate. You probably eat a lot of acetate. There's a lot of acetate in the sodium acetate, potassium acetate found in a lot of foods, preservative, taste, and so forth. So anyway, this page. So, and then the weak base, obviously, magnesium hydroxide. Magnesium hydroxide. All right. And again, what we mean by weak just means that these compounds do not dissociate 100%, much less 1 to 5% goes into solution. Yes, there are some ions in solution, but the bulk of it, 95% of it, is still intact. Okay. All right. So you may be given diagrams as follows, and the question would be, well, which one is a strong acid? Which one's a strong base? Or a weak acid? Which one's a strong base? Well, the last question, if you think about it, just by the definition of the base, Arrhenius definition, there's no OH in there, so I can't really say it's a strong base. Okay. All right. So, which one do you guys think is a strong acid here? Strong meaning literally 100%. What have we got here? Exactly, right? A would be correct, because if you look at A, literally all of the HA is dissociated. You don't have any HA intact. Okay. A weak acid, would that could be B and C, right? Because you can see B and C that we do have some HA still intact. There's some right there. They're still intact. Right there, intact. But there's only like one pair of ions in that case, and there's 2 pairs of ions in the case of B. So B and C would be weak acids. Right. And HA, who knows, it could be anything, you know, but there's no strong base here. Now, if I needed to compare B and C, which one do you think would be a stronger acid? Okay, which would be? Okay, yeah, B, I concur. B, simply because we have more protons in solution for B than we do for C. Okay, All right, good. Let me here. Now, with respect to what we do when we talk about pH, we're going to talk about pH because of acids and bases. Okay, pH is nothing more than a numerical scale, and it's related to the concentration of the proton in solution and the hydroxide in solution. Now, our scale runs from 0 on the far left all the way to 14. Keeping in mind, it's a numerical equation that a numerical value that we're going to talk about here in a second. Now, neutral is 7. Now, anything less than 7 with respect to the pH is classified as acidic. Anything greater than 7 is classified as basic. Now, from that point, we have weakly acidic and strongly acidic. You can see that about less than 2, roughly. It's a very strong acid material, literally 100% dissociation. Okay. The same is true on the other end of the spectrum. We got areas of weakly basic and all the way to strong basic solutions. Now, what they've done here, they introduce a concentration unit a little bit early, and they haven't really defined it. If you look at the bottom, you'll see a proton and hydroxide in brackets. Okay, right here. Okay, so right now we're going to keep it, just call it concentration. We're going to define it more specifically in a second. So you got the proton concentration. When the proton concentration is greater than hydroxide concentration, you're in the acid range, okay? When the concentration of each is equal, you're in the neutral range. When the hydroxide concentration is much greater than the proton concentration, then you're in the basic range, okay? There's another term they use, alkaline range. Now, thinking of alkaline, let me ask you something. I mentioned to you what happens when the proton reacts with the hydroxide. It neutralizes to form water, okay? Now, there is some water out there that you can buy. It's called alkaline water, okay? I believe the pH is somewhere around 8. Yeah, not 100%, but I'm fairly sure it's around 8-ish, close to maybe 9-ish, somewhere in this region here. Okay, so you buy it and then you drink it. Now, what do you think is going to happen once it hits your stomach? Once it hits the liquid inside your stomach, I should say, which is loaded with hydrochloric acid proton. Yeah, it will mess with the acid. In other words, another name for that would be it would get neutralized by the acid. Just like if you were to ingest Tums or milk of magnesia, it will react. That's a base, and so it would react with the acid in your stomach and neutralize it. And so I hear a lot about the benefits of alkaline water, and I haven't found anything with respect to benefits because the moment you ingest it, it gets neutralized. So I don't know where it would be. I know you'll create a lot of salts. And if you are, let's say you got high blood pressure, you got to be careful with sodium, especially if you're making a lot of sodium salts, that could be not be a good thing for you. As far as the water pH, back when I was teaching in Kansas City, I got a question here. I could see it helping with heartburn. Yeah, definitely. It will make it neutral and help with heartburn. Yeah. Now you got to be careful, if you change the pH of your stomach too much, then we got another problem. Because the pH of your stomach is that acidic. Your stomach is around 1 pH using the scale here. And that's because what chemicals, compounds at a certain pH have a certain configuration. And therefore, they need that configuration to function properly as enzymes so they can break down all the components and all the material that we ingest. As the pH changes, the configuration of the chemical changes, and those enzymes may not function properly. So you gotta be careful. But even though it's quite acidic, you have to ingest quite a bit. Water around, at least in the Kansas City area, I don't know about Arizona, but I suspect it to be like this. But I used to have my students from the Kansas City metro area bring a sample in of water from tap water or whatever water source they were using. And I was really surprised with respect to the range of acidity. I recall water being as low pH as 6 and as high as 11. And I'm like, wow, pretty wide. Okay. So I don't know about here. Be a good experiment to do someday. Find out from, is Glendale water any different from, say, Chandler, pH wise, so forth. Anyway, let's go on. I do know this, way back when in my undergraduate days, I did take a bottled water. We have hard water. Water is normal, 7 pH. Okay. So you're neutral. That's good. Now be careful when they talk about hard, they're talking about the concentration of other ions. And so if you have issues with sodium because of hard, you got to be careful with ingesting that. Now, way back in the 80s, as an undergraduate, I did look at bottled water because that was a big thing coming out, as far as buying bottled water. We're analyzing the pH, we're looking for organics. And it sounded good until we start looking for what are called volatile organic compounds, VOCs. These meant organic compounds in bottled water. They were loaded with all kinds of other organic compounds in the bottled water, even though they were saying natural spring and everything was good to go. So hopefully they cleared that up. All right. So here's a pH scale going from 0 to 14. Okay. All right. Here's what we mean by concentration. The brackets represent a term that we're going to become part of that term we're going to use quite a bit. And that's the unit moles per liter. For right now, we'll just leave it as the brackets represent molarity. Okay. And it has a units of moles per liter. And we're gonna get to learn more about moles, I believe next chapter after that. So as stated earlier, that the moles per liter of the proton is equals the hydroxide moles per liter or concentration or the molarity. And we have pH of 7. And normally pure water is that. But again, it varies quite a bit. When the proton concentration is greater than the hydroxide concentration, okay, it is classified as acidic, and vice versa. And the converse is true. If that proton concentration is much less than a hydroxide, then it's classified as a basic solution. Okay. Now, as I stated earlier, this pH scale is nothing more than a mathematical number. It's a mathematical function. It is defined as the negative log of the concentration of the proton. Okay. So, for example, if you had the concentration of the proton of 0.1, the pH will be 1. Now, let me share with you my calculator real quick. No, maybe not. Where'd it go? There it is. Okay. And so you notice on the calculator, there's a log button, log, which is cool because I remember having to do the looking up charts to figure out the log of numbers, or using a slide rule 100 years ago. Anyway, if I take that 0.1 and I type it in 0.1 and I hit the log, guess what I get? A negative value, a -1. And that's why there's a negative in front of the log, because that represents a -1. So a negative times a negative, guess what? You got a positive value. Okay. So the pH ends up, well, the majority of the time, you're going to always have a positive number for pH value. Okay. Can it get below? Yes, it can, but not very often. Okay. And so a negative, the log of the proton concentration, you'll end up with a negative value, and then you multiply by a negative to give you a positive. So if we do like 0.01, take the log of that, you get a -2. Okay, notice the pH is going up as the concentration goes down. We started off with a 0.1 molarity or concentration. That pH is 1. We go smaller, 0.01, concentration gets less, pH goes up. Okay, 0.001, concentration in proton gets even further less. Guess what? pH of 3, pH is going up into the neutral. Okay, so 0.00001, very low concentration of proton. Guess what the pH is? 5. Okay, and, well, the log is -5, but you got to multiply it by a negative. So you got 0.1, 2, 3, 4, 5, 6, 7, 0.0000, pH 7. Okay, or neutral. Okay, so that being said, we can see that a 0.0 -5. The other aspect is too, if you just take this is 1 × 10 to the -5. Okay, so you can convert that back to a decimal number, 0.000, etc. Or keep in mind, the fifth represents how many decimal places across you went. So basically, the pH is 5. For a concentration of 1 × 10 to the -5 moles per liter. If it's 1 × 10 to the -8, guess what? It's a pH of 8. The concentration is very tiny, 0.00, 8 decimal places. pH has gone up. Okay, we're in the alkaline. At a 5, we're in the acidic range, weakly acidic. At the 8, we're now in the alkaline region. 1 × 10 to the -3, pH of 3. Okay, which is also 0.001, -3. Excuse me, -3 times negative gives you a pH of 3. Okay, and then finally you can do this one here. Just count the decimal places, put it back in scientific notation, and you end up with a pH of 8. Okay. Now you can work both directions. If you have the pH, you take the negative pH and you calculate 10 to whatever. You have a calculator button that says 10 to the X power. You can input your pH value as a negative, and that will give you the concentration of the proton. That's called the anti-log, the opposite of what you did to take the log to get back to concentration. All right, some ranges of pHs. Obviously, vomit is very acidic, obviously, because of your stomach. Okay, and that's why it also burns as it goes up your throat, because the tissues in your throat, your esophagus, are not made like the tissues in your stomach to protect against high pH. you know, so it burns. And lemon juice, roughly about 2.3. Oh, is it time, guys? Yes, it is. Saliva, that ranges, depends on the person, but blood, very crucial pH. Very crucial. We try to maintain that pH, or otherwise we have problems. Milk of magnesia, which is mostly magnesium hydroxide, obviously 10 and a half, of course that will vary. Ammonia, about 11.7. Urine, again, that varies depending on the what you ingest and so forth. Most soda pops run from 2.5 to about 3.5, which root beer, I was surprised, is quietly weakly acidic. Okay, so anyway, what I'm going to do is stop it here. Let me stop it here on page 10. We're halfway done. We'll knock it out on Thursday, and then you guys can go ahead and pack your bags and head out to the Bahamas. Okay. Anyway, let me stop here, page 17.